Welcome back, my steel design friends. Over the course of the last couple of videos, we've been talking about column strength and how we can use the AISC equations as well as the AISC tables to produce a result in a very quick manner. However, there are some exceptions to this methodology that we need to talk about today. In particular, what happens if a column is braced in one direction or another? How do we adjust those tables, since there was the requirement that it was only with respect to the y-axis that most of those tables were set up with. In this video, I'm going to explain what those differences are and show you how to handle them. So without further ado, let's get started. So to recap our ongoing example problem that we've been looking at, we had a column that we've been designing for here that was pinned at both ends, had a length of 16 feet, and had 95 kips dead load and 100 kips live load. And through our analysis of this column, notice that there's no mention of the orientation of the member. You know, which way is the x-axis, which way is the y-axis. In this case, it doesn't really matter because we assumed L was the same for both. All right, so we have found that the factored load was 274 kips. Okay, we know that our K factor in both directions we're taking as 1.0 because we assumed it was perfectly pinned. Okay, and so our KL that we went into the tables with was 16 feet. Okay, and so if we were looking for, you know, an A992 beam, we could have gone, and this is how we did it. We went back to our W8, okay, and we basically went looking for 200, came over to the 16 feet and read over all the way over to the first W8 section that had a number in the LRFD column greater than 274. In this case, it's 275. Now, admittedly, in the previous videos, we talked about why I might not choose this one because the values are so close, but let's just go with the assumption that this one is acceptable and we're willing to live with it. All right, so we use the design tables, and you see that it's a very easy process to analyze a column using the AISC design tables for columns. We're in the 50 KSI column, so our 50 KSI tables, so we need to make sure that we're in the right tables. You'll notice even on the next page, the 65 KSI tables start. So make sure you're in the right one here. But the biggest note to make note of in this has to do with this note here regarding the effective length, what they're calling LC, the length of the column. Okay, in reality, this is K times L. Okay, but notice that these strength capacities are taken with respect to the least radius of gyration, Ry. Okay, as you know, for an I-beam, the IY value is typically a smaller value than the IX. Okay, which means that the radius of gyration, Ry, is smaller than the Rx, meaning that it will buckle in the weak direction, as we talk about, you know, strong axis, weak axis in previous videos. So this weak axis buckling, the IY typically is what controls, okay? So for a column that has the same length in both the X direction and the Y direction relative to its ability to buckle, you know, the weak axis is the one that controls. But what happens if I provide support in the weak axis but not in the strong axis? Well, now the tables start to break down, and so we need to kind of talk a little bit about that, and that's what the purposes of this video are today. So if I set this aside for a second, all right, we're going to come back and let's, you know, go through and assume that we've gone through all of our problems and, you know, did our analysis and are playing with our tables. You know, this looks like the table that we generated last time. Okay, and so we had our W8 by 40, a W10 by 45, a 12 by 45, and a 14 by 48. These were the same ones that we picked off of the video last time. Okay, I think the page number is different now, but the sizes still all work. Okay, and so we could choose to use the W8 by 40, which that video said 275. Older editions of this book said 276. It's right in that range. Okay, but what happens is that for the column as we had it defined in this example, L in both the X and Y directions with respect to those axes are the same length. They were all KL times 6, it was 16 feet for both. But what happens if for some reason our building is framed a little bit differently? Okay, suppose that we wanted to consider a situation where in the X direction it was still free, you know, it was still free before we had 16 feet and it was able to bow in this direction. Okay, and this was called as a weak axis because if I look at the cross section, notice the dotted lines that represent the web. This is the orientation. It's in an I configuration. So when this buckles, if I look at this y-axis and now I consider it over here in its buckled position, say out here at the middle, that's where the new y-axis is located. But the x-axis is still on the same line. That's how you know that this is a weak axis problem, that it's the y-axis that's done the moving on this. Okay, so one of the tricks that we do in structural design is that when I have a y-axis beam that is, causing, that is experiencing a failure, that it's controlling, that sometimes I will provide some bracing into this column in order to reduce the length. So here, this was my L value, right? And we assume, so KL here was 16 feet. Okay, now if we assume that we have we can put a beam in the mid height of this and assume that it is able to establish, a pin connection there, through some connection of the web. Now, again, whether or not that is really what's happening, that's a discussion that we'll cover in another video. But let's just say that, we now have two columns that are pinned at the top, pinned at the mid height, pinned at the middle, and it's free to rotate. Well, now my lengths are 8 feet and 8 feet. Okay, and so we now have different, what we call, unbraced lengths relative to the column. Okay, and in fact, relative to the weak axis, we have an LY1 that's in the upper of 8 feet and an LY2, which is 8 feet in the bottom. And you would have to design this column for both of these. Okay, now, in the case of it being in the middle and K being 1 at top and bottom, these two guys are exactly the same. But if this beam were down a little bit, say it was 10 foot and 6 foot, now you've got to look at, well, the 6 foot is stronger than the 10. It would be the 10 that controls. So you've got to kind of be mindful about this idea that K times L is going to be a factor going forward that we have to keep our eye on. And really it's not just K times L. Okay, it's actually KL over R. That quantity is the factor that we're looking at. So by playing this game, I'm effectively playing with the numerator of this. The R is still consistent. So what happens is that if I brace this in one direction and I don't do it in the X direction, now you have the problem where in the X direction, my unbraced length of this column is 16 feet. And so my KL, in the X direction is 16 feet times 12. And now, again, there's an implied 1.0 hiding in this equation, okay, which tells me that it's 192 inches. We calculated that last time. Okay, in the Y direction, though, we now have, instead of 16 feet, it's 8 feet. And so my LBY is 8 feet. Okay, and if we look at KLBY, that 8 feet times 12 is equal to 96 inches on this. Okay, and so it's a much shorter column. And if you look at the AISC tables, a column at 96 inches or 8 feet is much stronger than a column that's at 16 feet. Okay, and so now the question becomes, well, if we're looking at this ratio on here, which one's the worst value, KXLBX versus RX, or KYLBY versus RY? And the answer is we don't know. And the thing is that the tables that we use will not answer this question. They were sized for this one. But if this is the controlling factor, if this is a larger number, meaning that it's weaker, now how do I get those tables to work for me to be able to use them? Because it's a common problem that occurs, that we provide a bracing, whether it's, a beam from another floor coming in and bracing the column, or maybe it's, maybe I have some sort of, kicker coming down from a beam to help brace that column, kind of a K-brace, chevron brace kind of arrangement. All of those can be used to help protect this column and to keep that point from moving. All are valid techniques. So this is a common occurrence that we're looking at. So this is how we handle it. Okay. So the question becomes, how do we know which controls? Okay. So we've got to check both directions, strong and weak axis both. And this is the note to remember. You have to check both every single time. Okay, so for the Y direction, and normally this is what I do in the design process, is I assume that the Y direction is the one that's controlling. Because more often than not it does, but not always. So we're going to assume, just for the sake of argument, that the Y is controlling. We're going to come in and choose a size of, take our KL factor of 8 feet, okay, and a load of PU equal to 274 kips. And we're going to go back into our W8 table. Okay, and we're gonna size all of them in kind of a similar fashion to how we did it in the last video. So if you need a review, go back and watch that video. We're gonna go kind of quickly through this process now that you know how to do it. All right, so instead of being on the 16 line, I'm now on the 8 line. Okay, and I'm looking for 274 kips minimum. So if I come over and I tick all the way over to 18, the smallest number I get on the 8-foot line is this 348 at a W8 by 31. Okay, so it's significantly over designed even at that. Okay, but our standard column tables, if I wanted to go choose a smaller W8, I could. I'd have to go run the calculations by hand. But if I want to use the tables, we would say W8 by 31, let's go. And this is actually a fairly common size in a lot of buildings. Okay, smaller grade commercial buildings. So if we look at that, that's what we're looking at trying to do. Okay, so now if I repeat the process, that was how we got the W8 by 31. You could go through and do the same thing for a W10 by 33, a 12 by 40, or a 14 by 43, and these would be all the values that you would find in the table if you pull them out. So not only did we end up now, remember before we were at a W8 by 40, right? So I've saved about 9 pounds a foot on the column, and I've gained about 70 kips in capacity, right? Because we've protected that weak Y direction, okay? But we still need to check the X direction. And so for the X direction, okay, we have to make, an equivalent, because this is the entry value, or really KLY is the entry value into the column tables, but it's really this calculation that's controlling. Okay, we have to come up with an equivalent KLY equivalent. Okay, and so the way that that's done, in order to be able to use the tables for X dimensions, you have to put a correction factor on this. Okay, and so we're going to say that the KL for the Y equivalent length, which this is what I need to go into the tables to look at, I take my KL for the X direction, which in this case would be 16 feet, right? And now I'm going to divide it, okay, by an RX-RY ratio. And those values, you could either pull it from by hand, or at the bottom of these column tables, you will see way down at the bottom, okay, that for my W8 by 40, it was this column, and for my W8 by 31, down here, there's an RX to RY ratio value that's right here, okay, and that's the factor that you need. Okay, so for us, for a W8, we'd be looking at something like 1.73. And if you look at these are fairly consistent across the depths. If you go to the 8s, it's 1.7. Okay, if you go and you look at, say, the 10s on the next page, okay, you can see that several of them are sitting at 2.15, 2.16, and then we go back to 1.7, and then all through, some more of the larger 10s, that's a 1.71. So the families are kind of clustered together pretty well. So you get kind of a sense of what these ratios are for the different sizes. So what I've done is I've gone in and kind of said, okay, well, since we don't know what size of column we're looking to use, I mean, we've chosen one based off of the Y direction, but if we kind of go in and look at, some sizes, what we know is we know that, I can get a fairly small W8 size in here. So if I go back and I look at these RXRY values, for the 8 families I just showed you, 1.73, 1.74, this would be a pretty safe first guess. For the W10s, 2.15 would be the lighter 10s. Okay, W12s, you'll see it's 2.6, W14s, 3.0. Again, there's some play in this, but it's kind of a dirty feeling on this. And what you see is that a column that has a KXLX equal to 16 feet, in the X direction, has a similar strength to a column that is now, I take 16 and I divide it by this ratio number, would be the same as a Y direction column of 9.2 feet. Okay, that would be the equivalent Y length of column to be able to go into the tables and be able to use those. Okay, the W10 is 16 over 2.15, that gives me 7.4. 16 over 2.6 gives me 6.1 feet, and 16 over 3.0 gets me 5.3 feet. Okay, and so right here, we can see that if we were to choose the W8 on this, I have my KLY, and this is what we're calculating, is KLY equivalent using this KX guy, or KXLX value on this, that when I calculate this KLY equivalent in this column, I have the KLY equivalent of 9.2 feet and a KLY of what we were saying was 8 feet up here. So here was KYLY equal to 8 feet on that. Clearly, this column is weaker than this. Not by much. It's a little bit longer, so it's actually, the X direction is actually a little bit weaker if I brace that mid height on this thing, okay? And so we can go through and we can double check now, and we can start to choose our sizes. You can see that for the larger 10s, 12s, and 14s on there, KLY equal to 8. Now it's 7.4, 6.1, 5.3. The X is still actually stronger than the weak direction on those, but this little guy right here is the one that we're kind of playing with. All right, so if we go through and we look, the thing that you have to do is once I have the 9.2, what we're going to do is we're going to come back to our 8 table, and we're sitting on page 4-24 on this. And so instead of being at 8 feet, we said our dimension was 9.2. So I only have a 9 and a 10. I can iterate between those. Normally what I do is I just round up to the next larger foot. Okay, and then I can read over, so what is the strength of a column on 10-foot length? And if I read over, he's still worth 317. So this column would still be okay in the X direction at 317 kips of capacity. And that would be the design strength of this particular column now that we've corrected the tables. Okay, so it's a little bit of a correction that's required. Okay, it becomes a major issue when your K values start getting larger and larger, that you can end up with a K, a KLX that is off the table, but the equivalent brings you back onto the table. And we'll show you that in the next video as we start to kind of take a look at that. But that's what we're looking at and how to make this correction. It's this KLY equivalent factor that we see down here. This RX to RY ratio is the trick to being able to undo or to use the tables even for X direction. And you have to do it every single time. All right, so if we look at what we have now, so our column is still 16 foot long, okay, so we're bracing it at the mid height, so that would be an 8x31, 16 foot long if we assume $1.50 a pound, which is kind of a running number for A992. My students have kind of confirmed a sense of that number. The cost of this column will be $744. Okay, if I go back to what we had before, an 8x40 by 16 foot long at $1.50 a pound, that was $960. So you're saving about 25% of the steel in terms of cost alone. Now, obviously, if I go and I start having a connection in the middle, there will have to be bolt holes or drills. Is that worth the money difference? That's a decision or a discussion for another day. But as far as strength goes, that's how you make the corrections to the strength calculations for this. All right. Okay, so I hope that's kind of showed you how to correct the AISC tables to be able to use them to design both X direction and Y direction. One of the biggest challenges we have to figure out is understanding which direction and which axis it is that we're looking at that's undergoing the deformation. And that was the discussion that I showed you back on this last page down here. You've got to understand what's going on with the direction. So what I will normally do on this, just to kind of illustrate, is I will typically take a value, and I will grab a sheet of paper here, sorry. Grab my straight edge off the table here, okay, is you've got to get kind of a sense of, maybe I have, I tend to draw both sets of drawings, and what's framing into what. So let's suppose that I have a column that is, they've come up with an architectural set of plans. They haven't designed the columns or done any of the details yet. And then I'm looking at doing something that looks kind of like that, right? And just for the sake of argument, we'll say this is pinned, and then these are the floor beams. And so this is kind of a corner column, if you will, on this particular structure. Again, may or may not be realistic. I don't know. It doesn't matter. We still need to be able to know how to analyze this. Okay, so the question that you have on this column is, do I orient it this way, where the flange braces that beam, or do I orient it this way, okay, where that beam is bracing the web? And again, it has to do with the direction. And so the way that I start to see this, and this is, I'll spend a little bit of time kind of showing you how I draw this stuff out. Let's just, for the sake of argument, just kind of draw this, and in the X direction, if I turn it so that it is, so that my column is oriented in that direction in this picture, if you will, okay, if I'm looking this way, this is the view that I'm seeing, okay, and then at this height in the X direction, I would have, here's the beam at the roof, Okay, and then here's the beam at the mid height. We'll kind of look just like that, and then we assume that this is pinned. And just for the sake of argument, I'm going to put a roller on that just to say that this building is not subjected to side sway. Okay, in reality, it probably is, and we'll have to talk about that in the next video. What do I do when that's not the case? Remember, our assumption so far is that our K-factors are based off of a column that is restrained at the top and the bottom and is free to do whatever. Well, we know that in this column, for it to buckle in this plane, you would see something, if this is my center line, something like this, then this would probably do something kind of, that I would get a bow this way, and then I would build an S shape this way. Okay, so let's just say that this was my 8 feet, and this was my 8 feet. Okay, the axis that this 8 feet refers to then, this is an LX dimension. That was the LBX. All right, because it was the x-axis that when it buckled, again, we're looking at this axis, and my orientation of this column looks something kind of like this. Relative to the column, that's the x-axis. And so when it moves over to here, it's the x-axis that's moving. That's how I know it's an LX dimension. Okay, so you've got to kind of understand the deflected shape. Let's look at the same column looking in the other direction. All right, and so now I've got this guy. All right, and I'll put this one here. And again, just lay in some hidden lines just so we know that the web is happening here. Okay, and so now I'm looking at the column on this one. Okay, and according to the framing, if my column is oriented like that, I'm looking at the first one. Then the framing that's happening consists of a beam that's coming in. And again, I'm assuming the beams are all following kind of an I configuration, that somehow that's coming in and being connected to the web. It may be running over the top, whatever, but that would be the connection that I would be seeing here. Okay, and then again, we're doing a pin here, and I'm putting a roller here just to kind of help us with the assumptions. Okay, and now again, my column is looking like this. This guy clearly is going to bow something like that in its plane, in the weak plane. And so if I take that line, the axis that's down the center, that's now a y-axis. And then the line that is happening here, okay, that would be my y prime. That would be the new location of the y-axis. That's how you know that now what happens is my ly on this picture is 16 feet. Okay, so if we look at this, on this particular diagram, I have an LX of 8 feet, okay, and an LY of 16. And in reality, if my LX is 8 feet, then when I do the KLY equivalent, it's actually a number much smaller than that. It'll be like 3 or 4 feet or something. Clearly, this guy would be a whole lot stronger than this direction. This will be the direction that controls. Okay, so this is why instead of orientating it this way, I'm strengthening the x-axis, but it's the y-axis that's starting to control for me, right? So instead, a better option would be to turn it this way. Okay, and let's just, like I say, real quick, kind of sketch these things down. I know you guys love watching me draw, but I think these images, and this is the way I do it, just to kind of be able to visualize which axis it is that's moving. Now in this direction, now we're looking at the case where I turn the column so that it's oriented that way, doing the other option. Okay, and then here's my beam. There's my beam at the top. And then I come down and I put another one here. Okay, and I come in and do this guy. There we go. And put this down here. Okay, and so again, just like before, put a roller. Okay, put a pin. Okay, and this guy is going to still deflect in an S shape because we've restrained the middle of it, something like this. But now, again, my column is oriented this way. Whoops, I need to pull this up a little bit. Sorry, got way off the page. Okay, so here's the deflected shape. Just like what we did before, it's just I've turned the column direction. Now it's now in the I configuration, and the axis of the length of this thing, that's my y. That's my y prime. So it's the y-axis. So this would be an ly equal to 8 feet. This would be an ly equal to 8 feet. Okay? All right, and then if we go through and we look at the other side then, just to be complete in what we're doing, and then again, not the best sketch, but you guys get the idea, I hope. Okay, there's the top of the column, here's the bottom, pin, roller to restrain it. Okay, and then now we have this connection for this one, and then there would be this beam kind of happening up at the top. Okay, and that will be our case. And now this column wants to do this. Our column is oriented like an H. Okay, that's my x-axis, meaning that this is an x prime axis. That's the one that moves. So that's how I know that this Lx is now equal to 16 feet. Okay, and this was the example that we just worked, in which we said that for the shapes that we were playing with, that the KLY equivalent was equal to 9.2. All right, and you can see that these are a lot closer together. All right, so what you're doing when you're comparing these and determining which way to turn a column is you have to look at the orientations, and you want these two numbers to be as close to each other as possible, instead of the first case, which, like I say, I haven't run the number on this, but I'm guessing that KLY equivalent would be somewhere on the order of 5 to 6 feet, maybe. If I took that divided by 1.7, yeah, probably more like 4.5, but no, let's just say 5 feet on this. Okay, 16 versus 5, or 8 versus 9.2. Which one's more balanced? Clearly this one. And so this would be the optimal orientation for why I would turn a column and decide to mount it so that for this particular scenario, I would orient it this way. You know, and if I kind of draw this in 3 dimensions, down, 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 and then I would have this beam coming in, you know, there's the beam, like this, and then down on this level, I would have the other beam kind of coming in and doing something. Again, you kind of get the idea. I guess there would be another kind of, the bottom of the flange would be here. Okay, where this guy is oriented like this guy is oriented like that, you know, and then we would need that one, and there's the drop of the flange, kind of looks something kind of like that, and then this one would pick up and come over this way. I know it's a lot of sketches, and I hope it's somewhat clear to you, and then this one is running that direction. And that would be the way that I would orient this column, kind of with a 3-dimensional view. Kind of a 2-dimensional column, but a 3-dimensional view is kind of a weird thing, right? All right, and then there's my flange just to get it right. Okay, something that kind of looks like that. And that would be the way that I would look at orienting this particular sketch for the generic problem that we have here. This is one of the first things we have to do as a structural engineer, is we have to look at this and figure out which way is this column. Okay, this leads us to another conversation that on, you know, if you're using any sort of software, such as, you know, STAAD or RISA or ETABS, RAM Steel, whatever the case may be, any sort of steel design software, lots of times we put in our models into the program so that it looks something like this. Well, the strength of the building and the deflections and the performance of the building are dictated by the orientation of the members. You got to make sure you get that member put in right. In STAAD, you use something called a beta angle, where you can turn it 90 degrees, and I can actually physically change that, but you got to make sure you get this modeling right in order to be able to understand. But that's why we turn that column, okay, is I want these two numbers to be a whole lot closer together, because it's more efficient use, okay? Or at the very least, I want LY to be the smallest of all of them, okay, if that's the case, okay? Like I say, you can have, you know, cases where, you know, this example that we've used, the spaces were exactly the same. Again, if these were different spacings, you know, we use the idea of 6 and 10, or maybe it's, you know, 4 and 12 or whatever. Well, you have to choose the worst of these guys, okay, as well. So you're still playing the same game. If I brace the X direction at a place that's not in the middle, then I'll have 2 different X values, which means I need to calculate 2 different KLY equivalents like we did down here for each one. And then the longest one is the one that controls, okay, for those. So, all right, so that leads, hopefully it kind of gives you a little bit more clarification on kind of orientation of members and then how to use the AISC tables to fix it. Okay, in the next lesson, we're going to revisit effective length. I'm going to show you how to use something called the alignment charts that will, again, help us to address our estimations on this K value. Remember, right now, everything we've done, the top of this column is pinned. It can't move. In reality, that's never the case. So we've got to figure out, well, how do I fix this problem to be able to handle that? And that's the purpose of the next video. So stay tuned, and we will get that one up just as soon as we can. As always, if you got any questions, leave us some comments down below. Otherwise, if you found this useful, toss us a like on the video. We greatly appreciate it. And be sure to subscribe to the channel, and you'll know when more information is coming. So thanks for everything, and we will see you guys next time. Happy engineering.